Physics Notes, Unit 25, Geometric Optics. Basically the physics of mirrors and lenses. How do glasses work? How do microscopes work? Telescopes? Well, we'll start with reflection. Reflection is the bouncing of a wave. The bouncing of a wave. And it's pretty straightforward when you start with reflection. The law of reflection, the angle of incidence equals the angle of reflection. So incidence means incoming, and reflection means the outgoing. But let me back up a little bit, or give you the next thing here before I explain that more fully. All angles, when we're talking about angles here, we're going to be measuring angles, are measured with respect to the normal line. The normal. And in physics and math, the word normal means perpendicular. We talked a little bit about that when we talked about the normal force back with friction. So we have a normal line. It's very important in these problems that you measure everything, refer everything, and calculate everything from the normal line. In this first diagram here, we have the picture of a mirror, but this line right here, I'll highlight it in red, is the normal line. So that's the normal line. It's a line that's perpendicular to your surface. Now this, and then it shows you over here in green, angle of incidence. If you were to actually measure that angle is from there to there. The opening of that angle, that's about 60 degrees in this case, I'm just guessing. And that's called the angle of incidence. I'm going to call it theta sub 1, or sometimes they call it theta sub I. And then the angle of reflection. That's after it bounces, and if you measured that, if you took that same angle, okay, measured that opening, it'd be the same angle. Now, we'll be doing diagrams with what we call rays, or ray diagrams. Well, it says it right here, the ray model for light. Basically, this is not what light looks like. It's very difficult to draw light, once again, because it's invisible. We can draw that electromagnetic wave like we did in Unit 24. That's really cumbersome. So we simplify this just to basically show you with rays the direction that light is traveling. The wavefront model over here on the right is not very useful at all, but that could be a better indicator or picture of how water waves bounce off like a break wall or something like that, because water waves look more like lines if you look at them from above. But we don't want to do that. But what's also true is that if you relate the ray diagram to the wavefront diagram, bottom line is, that kind of shows you over here, I'm highlighting it right now, these two things I'm highlighting are the rays. The rays are perpendicular to the wave fronts. But we don't want to use the wavefront model. We could, but it's just too, like I say, too cumbersome. The ray model works really nicely for these geometric optics problems, explaining how mirrors and lenses work. We'll come back to reflection. We're going to spend some time on refraction and then bring it back to reflection. Refraction. Refraction is the bending of a wave as it enters a new medium. This happens for any waves: sound waves, water waves. Water waves when they go into different depths of water. That's kind of a new medium. Well, bottom line is, it's really more a factor of the change in speed. So water waves can change speed when they're in different depths of water. Well, we're not going to really do any water problems here as far as water waves. We're going to be doing light waves that go into water. But the idea here is refraction. Bending of a wave. We're going to focus on light waves. The bending of light waves as they enter a new medium, like glass or water. The bending is caused by the change in speed. When you slow down, it causes the light to bend, the waves to bend. And there is there's formulas, and then there's ideas and concepts that you'll have to understand as far as which way does it bend. When you go into something that's dense, I'll have this written down later on. When you go into a dense medium, it bends toward the normal. There's a picture of that right here. Going from air to water, this represents water. In this particular diagram, you have water down here. I'm going to just put this. So this is all water. So the air, that light up at the top is entering water. But I'm going to erase that. They have the interface there, this line of interface between the air and the water. But let me give you a few mathematical ideas first, and then we'll talk about which way the light bends. Does it bend toward the normal or away from the normal? So we have this definition for n. N is called the index of refraction, or the refractive index. N equals C. Okay, I'm switching back to red. N equals C over V, where C is our speed of light in a vacuum, speed of an electromagnetic wave in a vacuum, 3 times 10 to the 8th meters per second. V is the velocity of the wave when it gets into the new medium. So for example, when light goes into glass, it slows down. When it goes into water, it slows down by a certain percentage. We just take a ratio, however. We don't really use percentages. We could talk about percentages, but we're going to be looking at tables. There's 2 tables in your book that are going to be very useful. This is not from the book, this table. I'm going to use this table for the notes. You can find these tables online. They have published values for the index of refraction. And they're always 1.00 or greater, because the top number here, C, is the maximum speed of light in a vacuum when there's nothing to slow it down. The maximum speed limit, technically, once again, the speed limit in the universe. Nothing can go, no material object can go faster than that, in theory. We'll just go with that for now. There are people that are trying to disprove that, but that's beyond the scope of this course right now. But the denominator here is always going to be smaller than the numerator, so you always get a number that's bigger than 1. Furthermore, n has no units, because it's going to be a velocity over velocity. N has no units. You can see that in the table as well. But both velocities are in meters. Make sure they're both in meters per second. They cancel out. Alright, so what is the speed of light in water? This is a pretty straightforward problem. You just do N equals C over V. You look in that table there, and N in that table, or from the book, the index of refraction in water, let me double check that, is 1.33, which indeed it is, equals 3 times 10 to the 8th, 3.00 times 10 to the 8th, divided by V. So you switch the V to the left and the 1.33 to the right, so it's going to be 3.00 times 10 to the 8th divided by the 1.33, and you end up with a velocity of 2.26 times 10 to the 8th meters per second. So that's enough to be, substantial. It turns out if you do the math there, it's about a 25% reduction from 3 down to 2.26. It's roughly 25% reduction in speed. That's significant, because we say that the water is optically more dense than air. And the more optically dense it is, the more it slows it down. In fact, diamond, if you look at that table, is one of the most optically dense materials on that list. I think it is the most optically dense. It slows the speed of light down by over 50%. I actually have it written down here at the bottom. The index of refraction for diamond is 2.42. So if the number is basically a 2, that is a 50% reduction. Anyway, let's go back to problem number 2 before we go to problem number 3. What would the material be if the speed of what material would the speed of light be that value? Well, we're going to just plug in. All right, so we're going to try to find n. So we have 3.00 times 10 to the 8th divided by 1.95 times 10 to the 8th. And that gives us an n, an index of refraction of 1.54. So then we have to look at a reference table. Once again, the units cancel out. There's no units for n. It's an index. So we looked that up in a table. I think there's a couple that are close, and the closest one in the table is ruby. It's a precious mineral for rings and things. All right, so ruby. Okay, number 3. Okay, a certain light has a wavelength of 224 nanometers in diamond. What is its wavelength in air? All right, so one note here, it's very important, is that the frequency remains constant when light goes from air to water or to glass or in diamond. So that's the one thing that's going to tie this problem together. Now we have to go back to a former equation, V equals lambda F. In fact, I'm going to put some subscripts on here. Let me do it again. V air equals lambda air times the frequency in air, because we have to do this twice and maybe even 3 times. And we have V diamond equals lambda in diamond times the frequency in diamond. So the only thing that's the same in both those two equations is the frequency. I'm going to go way over here to the left because N equals C over V, because they gave me a diamond. They gave me 2.42 for diamond, 3.00 times 10 to the 8th over V. So V for diamond is, if you do the math there, 1.24 times 10 to the 8th. 1.24 times 10 to the 8th meters per second. That's the velocity in diamond. So I'm going to go way back over here to the right again. So that was step number 1. So just to kind of, that was basically my step number 1. I'm going to put a 1 over there for step number 1. Now I'm going to do step number 2 over here. All right. I have the velocity in diamond, which is 1.1. I'm going to go back to red. So I'll go to red. All right, it's now red. 1.24 times 10 to the 8th equals, it tells me the wavelength in diamond is 224 times 10 to the negative 9th. That's nano. Times the frequency in diamond. So you do the math there, the frequency in diamond, which will be the same frequency in both materials, 5.54 times 10 to the 14th hertz. All right, now I'm going to go to the middle here. That's why I'm using numbers to kind of show you how I'm progressing in this problem, because I'm going kind of back and forth here. The velocity in air is our 3 times 10 to the 8th. All right, that's our, air is like a vacuum. 3.00 times 10 to the 8th equals the wavelength in air, which is what we're looking for finally here, times the frequency, which is that 5.54, times 10 to the 14th. So this will give us the wavelength in air. Comes out to be 5.42 times 10 to the negative 7, but that's 542 nanometers. It's customary to put wavelengths of visible light in nanometers. All right, well, that wasn't too bad. It was 3 fairly straightforward steps, but you got to, the more steps there are, the more difficult it does become, even though they're easy steps. Okay, now Snell's law of refraction. It's got some symmetry to it. N sub 1 sine theta sub 1 equals N sub 2 sine theta sub 2. This then allows you to calculate angles of refraction, the angles at which something will bend when it goes into a new material. So it doesn't really have any, well, it has something to do with the speeds, because the n's, n sub 1 and n sub 2, are related to the speeds. But bottom line, and generally speaking, the more it slows down, the more the speed is changing, the more it's going to bend. All right? So basically, you're going to be going from it's always going to be 2 materials. You'll be going from, say, air to water, or water to air, or water to glass. They have to be transparent materials for light to transmit through. There's not a whole lot of transparent materials. They're in that table up there, different kinds of glass and water, plastics. So once again, we have the idea of a normal. We have to measure everything with respect to a normal. And now here's the fact that you have to remember. I'm not going to prove this to you, but when light goes into something that's dense, something that slows it down, it bends toward the normal. All right, so when you're going into something dense, well, if you look at, I'm going to do part B here first, all right, because what they're doing in part B, and there's a horizontal line here that is the separation between water and diamond. You can barely read this, water and diamond, but you're in the water, you have your angle of incidence. Here, this would be your angle of incidence. We don't need to calculate it right now. That's theta 1, or sometimes they call it theta sub I. I just call it 1 and 2. Theta sub I. All right? But that's got an index of refraction of 1.33, and diamond is 2.42, so you're going into the dense material. So here's how I kind of think about it. I wouldn't draw all this yet, but in my mind I'm thinking this. This would be the straight line continuation of the path, of the original path of the light. It's not going to follow that straight line path. It has to bend. And it bends at that one point right there when it enters the diamond. It's going to bend down this way. It's close to the normal now. In other words, this angle right here, theta sub 2, that's what we mean by bending toward the normal. That ray of light is closer to that dashed line, the normal, than it was before it entered. Theta 2 is smaller than theta 1, in other words. When you go into something dense, your theta 2 will be smaller than theta 1. That's bending toward the normal. As opposed to practice problem A here on the left, if you're in glass with an index of refraction of 1.52, going to water, which is less dense, once again, you can, in your mind, you can put this on here if you want. That would be the straight line continuation. I won't mark it wrong if you draw that on there, because that's what it's not going to do unless the two things are the same density. Then it'll go straight. If glass was 1.33 and water was 1.33, it wouldn't bend. But water here is less dense. So instead of bending toward the normal, it's going to bend away from the normal. All right, it's going to be something like this. Here's your theta 1. All right, now we have our theta 2, which is indicated by that double arrow I just drew there. That's theta 2. Theta 2 is bigger than theta 1. All right, let me give you one more sort of tricky one here. Let's do this. Let's have an interface here. Let's have an interface here. Let's say n equals 1.5, and here n equals, let's say, well, n1, that's n1. n2 equals 1.9. And we have a ray of light. We have a ray of light that's coming in like this. So now we got some kind of weird angles. The first thing you want to do when you're given these problems is draw your normal if it's not there already. So I'm going to draw a normal. It's going to look something like this. That's got to be perpendicular to my surface, my interface. So that black line there represents the separation between the two materials, whatever they are. They're two fairly dense materials, but material number 2 is more dense than material number 1. So the rule is if you're going into something dense, well, here's my theta 1. Theta 1 would be measured right there, my theta I, my angle of incidence. So instead of going straight, right, this one's going to bend down towards that normal. So theta 2 here is less than theta 1 because you went into something dense. We'll practice that a little bit more as well, because we have to get the angle with the right measurement with the normal. All right, so for example here, well, let's do a couple here. We'll draw these out as well. Just calculate theta 2, and they don't give us a diagram. So if they don't give you a diagram, the easiest diagram to do is just draw something horizontal. It says n1. Oh, this is n1 is 1.5. This is n1 is this is n sub 1. N sub 1, n sub 2 equals 1.1. So this is kind of the opposite of the one we just did. We're going to less dense. We're going to less dense. So it says theta 1 angle of incidence is 36. So if I draw my initial incoming ray, this angle here is 36 degrees with the normal. 36 degrees. My dashed line is the normal. And I'm going into something less dense than what I'm in. I'm going from n sub 1, 1.5 to 1.1. So if I think about this, I usually don't draw that. I just kind of envision that. But my bend is right here. This has to be like that ray, when it goes in, has to bend away from the normal because I want to something that's less dense. So in other words, theta 2 here, theta 2 has to be more than 36. So I just plug in now, n sub 1 sine theta sub 1 equals n sub 2 sine theta sub 2. Like I say, some books, this book uses 1s and 2s, or some books use I and R. Incidence for I for incidence and R for refraction. But anyways here, n sub 1 is 1.5. That's sine of 36 equals n sub 2, 1.1, times the sine of theta sub 2, which we're trying to figure out here. So I went ahead and finished that off. I multiplied the 1.5, multiply the 1.5 times the sine of 36, it's 1.08, divide both sides by 1.1, you get 0.98, and then take the inverse sine of 0.98, you get 79 degrees. And indeed, it's bigger than 36. All right, so let's go to this other one. Let's draw it. I mean, you don't always have to draw this. I'm going to draw a vertical line this time, just for something different. It says n sub 2 is 1.44. All right, I'm going to say n sub 2. N sub 2 is 1.44, and we don't know what n sub 1 is. N sub 1 is unknown. All right, so theta sub 1 is 31 degrees. All right, so I'll draw my normal line here first. So here's how a normal looks to a vertical line. It's horizontal. My theta 1 incoming. Oh man, that's not good. Let me see if I can get rid of that. Theta 1, much better. 31 degrees. Now it tells me in this case that theta 2 is smaller, so it did bend toward the normal. That's 15 degrees. So it tells me the angles this time. All right, so bent toward the normal, so I know that n2 is greater than n1. N1 is going to be less than. That'll work out in the math this time because you're just going to plug into n sub 1. You're going to have n sub 1 sine 31 equals n sub 2, which is 1.44, times sine of 15. So that's all set up for us. N sub 1 times whatever sine of 31 is. Sine of 31 is 0.515. 0.515 equals, and then you take the sine of 15 times 1.44, that comes out to be 0.609. So I took the sine and multiplied by 1.44. So then you just take 0.609 divided by 0.515, you get 1.18. Yes, indeed, it's less than n sub 2. It has to be less than n sub 2 because the light went from less dense to more dense. It bent toward the normal. Now, some other interesting things happen. You have this idea called the critical angle. And I'm going to use a diagram to help explain this. This only works when you're leaving a dense medium. You have something called a critical angle. So they're using water and air as the example here. There's three different examples of this kind of the same scenario. So you have light underwater here. All right, theta 1. And it bends away from the normal because it's going from more dense water into less dense air. Now, I'm going to draw another on that first diagram. If you were to draw the light going like this, the refracted ray would look like that. And if I drew it even at a steeper incoming angle, if the light was coming in like this, all right, oops, I want to use a different color. The light was coming in like this, it goes like that. So what happens here is you can see as I increase the angle of incidence from red to blue to black here, the angle of refraction increases, but gets closer and closer to that refracted ray, like in that last case I just drew, that refracted ray is almost on the water, on the surface of the water. In fact, that's what they call the critical angle. You keep going with your angle of incidence, and I'm pretty close to it with my black example over here on the left, where you have a refracted ray that's on the surface, and that's going to be problematic from a physics standpoint. Well, and not really problematic, but it's just going to be an impossibility, because that refracted ray is not going to be on the surface of the water. So what happens is you get reflection. You get internal reflection. Or what you really get, as you get that angle and beyond, you get total internal reflection. It acts like a mirror. Even though the surface of the water is not a mirror, it's going to act like a mirror. It's total internal reflection. Actually, just before you get to that angle, before you get to that critical angle, as you increase from red to blue to black, you start to have more and more reflection. There is some reflection. Back over here on the far left, even with the red, there's going to be some slight reflection. So I'm going to draw that as a dash line over here on the left. I drew a little slight reflection. There's always some slight reflection. But the closer you get to the critical angle, and the closer that refracted ray gets to horizontal or with that surface, the more and more reflection you get. And then this middle diagram is really an impossibility. That will not happen. You cannot have a refracted ray on the surface of the water. You have, instead, total internal reflection. So you have theta 2 equals theta 1. Okay, going back to the top mathematically here then. Well, not kind of, it is mathematically. Here, I'm going to circle it up here in the top. That's the condition that as you hit the critical angle, I'm using a subscript C for critical angle. That's the exact instant in which, if it could happen, the refracted angle, theta 2, is 90, sine of 90. At that very instant, you have what's called the critical angle. That's the definition of where the critical angle happens mathematically. Well, if you remember, sine of 90 is 1. Sine of 90 is 1. So you get n sub 1 sine theta critical equals n sub 2. The sine of 90 cancels out. The way this is usually written, though, is the sine of theta critical equals n sub 2 over n sub 1. It's called the critical angle formula. Make sure you circle that, maybe put a star by it. Critical angle equation. You could even say theta critical equals the inverse sine, because you have to do inverse sine of n sub 2 over n sub 1. This has a lot of practical applications. One in particular, over here on the right. This is basically the basis now of modern telecommunications. You've probably heard of fiber optics cables. What they do is they take thin fibers of glass. Instead of using copper wire, which is very expensive, even though glass fibers are more brittle, but they encase them. And what they do is they convert your voice through the electronics of your phone and computers, and convert it into light frequencies, light pulses and so forth. And they point your light, your signal, into a fiber of really like hair light. They're really hair-like, and they bundle them into like a bundle, like about a couple hundred. I'll show you a little picture of it here in a minute. And then these cables are buried. In fact, they're buried. There's hundreds of them buried in the ocean. That's how your phone calls get to Europe or to any other continent. Basically, it's through these cables. They don't go through satellites. When you make a phone call on your cell phone, there's the wireless part of the call that goes to a cell phone tower that's nearby. But that cell phone tower is connected to all kinds of underground cables like this, to different computers around different cities, and then across the ocean, under the ocean, not above, not to satellites. I'm going to do an example problem, then I'll show you a little video on this. But let's do a sample problem first. It says, what is the critical angle at the air-water interface? Well, that's pretty straightforward. The sine of theta critical equals n sub 2 over n sub 1. Okay? Where n sub 1 has to be greater than n sub 2. So you have to be in the more dense. So you got to go from water. N sub 1 has to be the water. So you always got to put the bigger number on the bottom. So the sine of the critical angle, and you can only have a critical angle if you're in the water going to air, or in glass, like that fiber optics. Glass is, well, air is always 1.0, so that's always the nice thing here. If it's always air there. It's not always air. but most of the time it's air. In these fiber cables, sometimes they have a coating on them, and then they have them wrapped up in rubber or like insulation as well. But the coating is going to have some kind of like 1.00 or some number that's smaller than the glass. And glass, I have to look up glass, hang on. No, I don't have to look up glass. This is water, 1.33. 1.33, it's not glass. But if it were glass, you'd have to put in the number for glass, whatever the number for glass was. But that then if you work that all out, you divide that and take the inverse sine of 0.752, and you get theta critical. If you do 2 steps there, 49 degrees. So yeah, you divide that, get a decimal, and take the inverse sine. The decimal is 0.75. I don't need to see all that work. That'd be plenty of work on the homework. Just show me the numbers you plugged in, you can give me the answer. But let me show you a little bit about fiber optics cables. So as the light bounces through these thin hair-like fibers, they are exceeding the critical angle at each bounce. So these things can curve. The light's not curving, the light is bouncing. But here, the ones that are buried in the ocean, or even underground, the ones in the ocean are pretty fancy because they have to have a lot of protection from the elements, from the seawater, from sharks or animals that might chew through them or whatever, or once again the corrosive effects of the water. But there's several layers here. I'm not going to get into all the layers, but in the very middle here there's little tiny hair-like fibers. And the thing is, they can send more than one signal through a fiber at a time. So they might have 100 fibers in there, but then they could handle like several hundred phone calls at the same kind, or data transmissions for the internet and so forth. Once again, our communications these days are not by satellites, they're by these cables. They're buried in the ground, all over the cities, from cell towers and under the ocean. Back in the day, late 1800s, they laid like a copper wire from like Europe into the United States. That was very expensive, and I don't know how long they used that for, but obviously it was much less useful, very expensive. I mean, it was useful at the time to send communications back and forth from continent to continent, but now this is like lightning fast. I'm amazed I can talk to somebody. We had a friend in China, and we could talk to somebody in China. It was like they were right next door. It sounded like they were next door, and the communication was that fast. I mean, they're like, 5,000 miles away, 6,000, I don't know how many miles, 5,000 miles away. And they're getting the signal just like that through these cables, because the light still travels very fast through these cables. Even though it's not as fast as through the air, the light travels really fast through these fiber cables. And it's amazing how they can connect them together and keep the signal strong enough. They have repeaters that kind of boost the signal every so often. Here's kind of a look over here on the right, how you have a whole bunch of them in one cable. That wouldn't be one that's buried in the ocean. This one over here is, I think, the style of what's buried in the oceans. Here's a world map. You can look this up. You can just go to, on Google and just type in buried fiber optics cables, and there's a map of, there's hundreds of these cables, and they're burying them as we speak. There's probably more and more being put in. There's about 5 or 10 or 15 that go from the United States to Europe, South America, and then from the western United States over to Asia, and then connecting all the other countries. And then there's all the ones that are buried in the ground on the continentals. These are just the ones that are buried on the bottom of the sea. So it's big business, and it's nice because it helps. It's a big part of the interweb, the internet. Once again, very little satellite communication with any of this. It's all through these cables that are connected to cell towers and switching stations that are attached to the cell towers and so forth. So it's quite amazing that this technology works. Physics works here very nicely to help us with our communications. Dispersion. Dispersion is the separation of white light into the constituent colors. Roy G. Biv, you've probably heard of that before, but that stands for red, orange, yellow, green, blue, indigo, violet. Most of you have probably heard that before. The colors of the rainbow. And once again, there's all different kinds of shades of different colors and so forth. We can get thousands of colors, but this, 7 basic colors there, Roy G. Biv. It turns out that different colors bend a little bit differently. It turns out that blue bends more than red. The index of refraction for blue technically is a little bit greater than the index of refraction for red, and accordingly, actually violet's the biggest. But usually when we talk about the spectrum, we talk about from red to blue. Even though blue is not at one end, it's near the end where violet is. So it turns out you can use a prism, and I'm sure you've seen this before. Well, we've all seen rainbows because raindrops do the same thing. I'm kind of illustrating that over here on the right. But prisms, because of the geometry of these things, when the light goes in, it starts to separate. It separates a little bit while it's inside the prism, and then when it comes back out, because of the angles involved, it separates even more. So you get this dispersion, the official name for the separation of white light into its constituent colors. And raindrops sort of do this. Well, they do the same thing. And this shows you light from over your head going into a raindrop, bouncing off the back of the raindrop because of total internal reflection, bouncing out the front, and this is your eye. This is an eyeball right here. Okay, so let me do one sample problem here. You have a beam of white light striking the equilateral crown glass prism that I have up there at the top, 35 degrees. What is the angle of separation between red and violet inside the prism? I'm going to draw a couple diagrams here and then show you how this is done. So I've done most of this. Here's our diagram. This represents white light. It's a red beam right there, but I can't draw a white ray. So that's all Roy G. Biv in this beam. So when it goes in, that's showing you the red separating at angle theta 2, but the different colors are going to be separated at different angles. If you go back to this diagram right here, okay, inside there, theta 2 for red is going to be smaller than it is for blue. Blue is going to be bent more, and violet more so than blue even. Inside there and even outside there when they come out, the separation even gets greater when they come out. But bottom line is I'm just applying Snell's law using these two different indices, and they're very close. Okay, so you might even say that the index of refraction for this crown glass is 1.52. Actually, if you look way back to that table, I'm not sure what it is in the table. I think in the table it says it's 1.52 for crown glass, if you look it up. But for red, the index of refraction is 1.512, so N1 is air times sine of 35, that was given in the problem. Index, the angle of incidence equals 1.512 times sine theta 2. You solve that all out, take the inverse sine for the last step, you get theta 2 for red. Red gets bent that much. That's how close it is to this normal that I have over here. That's the angle, which is, that angle with reference to the normal inside the prism. Well, if you repeat this process for the blue or the violet, I don't have violet markers here, I have a blue marker, so this is like violet. But instead of using 1.512, I'm using 1.530. That gives you a slightly different angle, a slightly bigger angle. So if I go back to this diagram over here, that means the violet comes out at an angle of about like this. Okay, so somewhere like this. So the theta 2 there is smaller. I'm exaggerating it. The question is, what's the angle between those two beams? Well, if the red was bent at 32.8 from that normal, and the violet 33.3, the angle between those two is, well, 33.3 minus 32.8, which we can probably do in our, well, we can do in our head, 0.5 degrees. That's their separation inside there. All right, and so it's not much of a separation. It's half a degree of separation, but it's enough to notice. Maybe not inside. Our eyes still can't maybe separate that, but when they come out, they separate even more to a degree or more. When they come out, then it starts to what we call, well, it's a visible dispersion. Dispersion is the splitting of white light into its colors, arranged in that order. And it's because of the different indices of refractions, or the different speeds of the different colors. The higher frequency, which is the blue and violet, gets slowed down more, because once again, the bending is due to a change in speed in that medium. And then some fun things about rainbows. Two main ingredients for rainbows, and we've all probably seen rainbows. We all know that we need sunlight. We need sunlight. We need sunlight behind us and raindrops in front of us. So it's after it rains. When the rain is off, usually in our area of the world, it's off to our east. We see rainbows in the east mostly. They can be in the west as well, but mostly in the east. All right. the sunlight is refracted. It's refracted into the front of the drops. That's right here. I'll go back down to the diagram. So that dot right there, right down there, that's where the first refraction occurs. We have white light from the sun, and there's some geometry to this. I'm not going to make you memorize these angles, and it spells out the angles in the book as well. But it refracts right here. There's some starts to be some separation like we just showed you with the prism. So it acts like the prism. And then there's total internal reflection. There's internal reflection off the back of the drop. All right, it's showing you that over here in the diagram right there. And as this occurs, you get more of a separation as time goes, or as the distance goes on, and other weird things happen. They kind of cross over each other inside the drop because the drop is spherical, and all. You can kind of see the geometry here. And then when they come out the front, once again, there's even more separation. So they're refracted out the bottom front. So there's 2 refractions, 1 reflection. Some of you know this. You can make a circle rainbow with a garden hose with your sprayer. Like if you go outside on a sunny day, take a misting, like a sprayer that has a misty spray, and you spray it in front of you. Well, if you put the sun behind you, and spray in front of you, you can see a circle in that mist. Sometimes you see this by waterfalls at the right time of day, where the mist is coming up and the sun's behind you. You see water droplets, the mist from a waterfall. That's kind of a cool effect. The secondary rainbow is, well, the geometry is here. Sunlight going into the bottom of the raindrop, reflecting twice, coming out the top. There's some other interesting things about the geometry of this. It turns out like this is a person on the ground, and there's a diagram kind of like this in the book. But double rainbows are not as common, obviously, as single rainbows, and they're usually not as bright as a single rainbow. But it takes thousands, if not millions, of raindrops in the sky for you to see a rainbow. You're not seeing the rainbow from one drop. These are tiny drops. For example, these 2 drops here, and they could be 7, Roy G. Biv, but right now, it turns out because of the geometry, and this is kind of explaining why, these 2 drops represent a primary rainbow, the basic rainbow you typically see. The upper one's way up here, because a double rainbow is even higher in the sky. And there's angles here that it's like 42. These are almost always 42 degrees, and what was it, 50-something, 51 degrees for the upper double rainbow. You don't need to memorize any of those angles. But here's the thing: for the standard rainbow, the regular primary rainbow, red is always at the top of that rainbow because drops higher in the sky are the drops that send red light. This is showing you red light going into your eye. Once again, you see stuff because light goes in. So this is red light coming from a raindrop high in the sky going into your eye, so you see red up there in the sky. And then that lower drop, the lower drops are sending blue into your eyes. That's why you see blue as at the lower part, or violet even lower, and green in between. They're not showing you the drops that have green would be like in here, between those 2. The opposite is true of the upper rainbow. The upper rainbow, okay, blue is the highest color based on the geometry, and red is the lower color in that secondary rainbow. So here are some, you can kind of see it here. Red is always the upper color in the primary rainbow, but if you look carefully at the secondary rainbow, red is the lower color based on that geometry. Rainbows are fascinating. They're awesome, obviously. There's another double rainbow, and red on top of the first one, and then red on bottom of the secondary rainbow. So that has to do with refraction and reflection. And off the back of those raindrops, it's probably, I think it's total internal reflection. It's total internal reflection because you've exceeded the critical angle. It wouldn't necessarily have to be total internal reflection, but the closer you get to the critical angle, the more and more total it is. But even once you hit the critical angle and beyond, you have total internal reflection. So we have Snell's law that explains refraction. Well, what it really explains refraction is the fact that light changes speed, or any wave, but particularly light, changes speed. If you slow down into a dense medium, you bend toward the normal. If you speed up, you bend away from the normal. The index of refraction gives you the ratio of how much you slow down compared to the speed of light. So the equation was n equals c over v. Alright, now we will get into some ray optics, more specifically how lenses and mirrors work with the principles of refraction and reflection.